The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Thank you for everybody coming back. I should tell you, when I start the session with that little shh, I learned that from a congressman in Baltimore. For some of you know, I've spent a lot of time around politics. And one of my roles in politics was that I was the treasurer of the Maryland Democratic Party, which if anybody ever asks you to be the treasurer of a state party, come, I can give you some advice about, what that's all about, but when your home state senator asks you to do it. So I had to quiet down the annual Jefferson Jackson Day dinners. I organized these big dinners, and there's 400, 500, 600 people at these dinners. I couldn't do it. I couldn't get their attention. And Congressman Elijah Cummings comes up, and he just leans into the mic. Shh. And it quiet the whole place down. I said, Congressman, what is this? Is this something you've learned in politics, something you learned from your minister, your priest? How? He said, it works every time. Works every time. So Elijah Cummings gave me that little duty. Blockchain and money. We're here. I know it's a little bit like eating broccoli these last couple of classes because we went through cryptography, and then we moved a little bit into consensus protocols. And today we're going to pick that up and try to finish up the design bits of Bitcoin. I wanted to introduce, though, one walk-in. We're going to have walk-ins from time to time in this class, but Patrick Merck, he's hiding over here with the cap and the hoodie. He's got the look for a lawyer who's been spending his time around Bitcoin for 7 years. Now, he's currently affiliated with Berkman Klein at Harvard. And I didn't know Patrick was going to be here, so I'm calling him out. He's also special counsel of the Cooley Law Firm, and he has a bunch of clients who try to do the right thing by the law, but sometimes they find themselves dealing with the Securities and Exchange Commission or other fine government institutions. But Patrick was also general counsel to the Bitcoin Foundation. And for a short while, you ran it, didn't you? Before it kind of went poof.
Yes.
Yeah.
Helped it go.
Yeah. But Patrick's the type of lawyer that wears a hoodie and a baseball cap. So he's a Bitcoin lawyer. So I thought you'd introduce, if you ever need Patrick for one of your entrepreneurial efforts, I'm sure his Cooley Law Firm will help, like advising you too.
Take Bitcoin?
What's that?
Does he take Bitcoin?
What is that?
Does he take Bitcoin?
I have.
Patrick, so
Often. In fact, I've never bought a Bitcoin, ever. But I used to get paid 100% in Bitcoin, so it's all good.
So Patrick, when you get paid 100% in Bitcoin from a client, how long do you hold it?
Well, it depends, right? But often in the early days, not very long, because I had to pay for my mortgage and my kids' daycare and things like that, and they don't take Bitcoin. So I've sold a lot of Bitcoin over the years, sometimes sadly, but never bought one, just earned them.
So you're like a miner, except for you're a lawyer who gets Bitcoin.
I mine with my mind.
The study questions for today was we were going to turn to that last piece about transactions and something called the unspent transaction output and script code that is a computer code that's used inside of Bitcoin. We're going to talk a little bit about the design features, bringing it all together, and particularly around the reading, which was the academic pedigree of Bitcoin, which is also a reading that Patrick assigns when he does his study group at Harvard Law as well. And then, yes, all of you are going to be able to participate, and we're going to take a survey amongst all of you as to who's Satoshi Nakamoto. Ah, yeah. Or would you rather do more on transaction script? All right, we'll do a little bit of both. The readings, of course, the Bitcoin academic pedigree, which we're going to talk about in the latter part, and I'll do a little cold calling and get some feedback as to what you thought from the reading, or if you're still skimming it. And then there was a CoinDesk article just making sense of it all. And so, as I said, we'll go through the transactions. We'll do a little bit putting it all together, and the academic pedigree. We'll have our little fun with you all are going to have a chance to tell us who Satoshi Nakamoto is, or was, or the committee. So transactions. You've seen this graph before, but transactions, the format in a transaction ledger, not only in Bitcoin, but really everything, is somebody on one side of a transaction and somebody on another side of a transaction. So in Bitcoin, there's an input. And the input inside of Bitcoin is an ID of a previous output. So not only is Bitcoin a series of blocks of information, each block that has 1,000 to 2,000 individual transactions, but in a sense, there's a separate chain that's going on. I sometimes think of a blockchain as yes, there's the chain of big chunks of data, but there's also a chain of individual transactions. Shimon, is that a hand raised or just scratching your head? That's right. Shimon is a faculty member of the finance department here at Sloan, and some of you might take his Finance 1 course. I assume somebody in here is probably. So the input is just really the ID of wherever the output was. And you can think of a chain of a transaction. Can anybody tell me where all transactions come from? Where's the sort of the genesis of the value if you follow a transaction chain back to its origin? Hugo?
Coinbase.
Coinbase. So anybody want to say what a Coinbase is?
It's a generation of a freshly minted Bitcoin.
Right. So the generation of a freshly minted Bitcoin, not the way that Patrick Merck got it when he's selling his services for the law, but how a miner gets it. They get their transactions. Remember, initially 50 coins was what happened initially back in 2009. Now it's 12.5 coins. In a short couple, maybe it's about 18 or 20 months, it goes to 6.25 coins, and it keeps splitting half and half and half, eventually to no Coinbase. But every transaction, in essence, had to go back all the way to Coinbase. Some Coinbase, some 50 or 25 or 12.5 coins being issued. And then the output. So a transaction format is pretty straightforward in a sense. The input is a previous output and a digital signature. And then to whom do you want to send it? And it's sent to Bitcoin addresses. That's why we spent just a moment. We just glossed over what a Bitcoin address is. It's sort of a translation of a public key, but it's not identical to a public key. And of course, you need value. Value measured in Bitcoins or Satoshis, or if we're on the Ethereum network, it would be in Ether and gas, et cetera, et cetera. On 1,600 different platforms, it could be a different native currency. Lock time. It wasn't, I don't think lock time was in any of the readings, but anybody want to tell me what a lock time is? Just so, because it's relevant to some of how the technology goes. Anybody want to take a guess? Where's Aline? Not Aline, the PhD, but Aline from the Digital Currency Initiative. No? You're hiding. You don't want to say what a lock time is?
I thought it's some sort of protection mechanism for. I guess double spending.
It is a protection mechanism, but not so much about double spending. Tom, did I see your hand up?
This is a guess. Is it when the transaction is hashed?
So it's when. It's about time. It's when the transaction can happen. So right now it's 2:45 on September 20th. If you put a lock time in at 2:50 or 255, it couldn't happen until 255. So you can actually conditional the transaction. That's all lock time is. But you can say it can't happen until. You could put tomorrow's date.
The counterparty said that, so it's like the date on a check.
It's a little different than a date on a check, because one of the things that gets validated in Bitcoin is that it will not validate a transaction early. And if you put October 6th on a handwritten check, the bank might still take it, even though they probably shouldn't. So it is like the date on a check, except it's verified and validated and so forth. Well, I'm going to take Emily and then Shimon.
So if you were to set the lock time in the future, could that mess up the blocks in the chain? Because like what is the kind of the right chain of events that you're recognizing if you're choosing to set a lock time in the future? I guess the broader question would be like, why would you set a lock time in the future?
Shimon, were you answering that, or you?
No. Only asking in the broad question, like, what purpose does it serve, right? So you're not really, it's not a really Turing complete language, so you're not really trying to create conditions here, right? So, but this is sort of a condition.
So it's a condition because at any point in time you might want to condition a payment. You might want to condition a payment on time. And we're in a few slides going to talk about the scripting language, the computer language that allows transactions to happen. Shimon said was not Turing complete. From the readings, anybody want to tell us what Turing complete is in computer science language? No? No idea. Anybody who know who Turing is? Anybody see Imitation Games? Right. Anyone know what the Turing Award is? It's sort of the Nobel laureate for computer scientists.
Isn't that the award when a machine can actually become, can pass as a human being?
Well, that's one thing associated with Turing, but the Turing Award is an annual award, sort of like a Nobel laureate, but for computer scientists. Turing Complete allows you to do loops inside of computer programs. And the script language does not allow that to happen. Every function needs to sort of have some language. I mean, I know Aline's looking at me to see I don't dive. But to answer Emily's question, it's just there's so many different ways to condition a transaction. And Satoshi Nakamoto thought, well, let's put in here right in the transaction format that you can condition on time. And then two parties could do that. To your question about whether it could inadvertently lead to double spending, it's a very good question. Can I hold it until we just do validation for a second? So this is a unique identifier for the input, but it's really uniquely identifying from a past output. What's the block number? Is it from the 250,000th block or the 300,000th block? So it takes literally a block ID. And then within that block, which one of its 1,500 transactions might it be? So you can find any transaction on an entire blockchain by knowing the block, and then within the block, which transaction. It's just a data mechanism on how to store data. And through this mechanism, there's a chain of transactions as well as a chain of blocks. And then the value, we talked about that, I think there's, if I did my numbers right, 10 to the 8th Satoshis in every Bitcoin. It's a little hard because I think there's 10 to the 9th gas in every ether. So. And that's a coin. That is what is a coin. When Satoshi Nakamoto did this, it wasn't really a coin because it was a question whether anybody would give value. And until about 18 months later, when those two pizzas went for 10,000 Bitcoin, you know, what was it? Or until somebody started the first exchange, a crypto exchange, to exchange that. So you can also have multiple inputs and multiple outputs. And I'm going to use an example that I just created of I want to send some Bitcoins to two different people, and I need some Bitcoins. So I might grab 3 former inputs, and these are just transaction ID 6, index 3. Of course, it wouldn't be ID 6, it might be ID 300,000. But the point being is, grab 10 Bitcoin, so I want to find 3 inputs. And I needed to send 6 Bitcoins, let's say, to Amanda. You like that. And just because you're sitting up front, James, I'm just going to send 3. But I'm not using Amanda's name and James's name. I'm using your Bitcoin address, Amanda's Bitcoin address, and James's Bitcoin address. So rather than being account-based, like if you have an account at Bank of America and you say, I want to send $10, I just check to make sure I have more than $10. In Bitcoin, I actually have to find individual transaction outputs that add up to, in this case, I want to send 9 Bitcoin, 6 to Amanda, 3 to James. Not really, Amanda, but so what's 10 minus 9? Thank you, that was really hard. We are at MIT. But I might not send 1 back to me. I'm going to send 0.9 back to me. This is kind of my change. So a Bitcoin transaction can either be equal, the inputs equal the outputs. I could have sent 1 back to me, but I've decided to incentivize miners and leave a little extra, 0.1 Bitcoin, which would be a lot of fee, actually. That would be about, what, $640 or so? I probably wouldn't do that. I would probably leave for a fee 10 or 20 or 100 Satoshi maybe. I don't know what the current market is. But this is a transaction, multiple inputs, multiple outputs, but you always have to send back to yourself. What happens to these inputs if this transaction actually happens? They go away. The actual inputs disappear once they go through this. And so inputs always have to equal outputs. When a transaction is validated, one of the validation methods is to make sure that the lock time has actually happened, that you've passed the lock time. Another validation point is that inputs are greater than or equal to outputs. If outputs are greater than inputs, the transaction will not be validated. The digital signatures have to be validated, back to going just back to the prior slide. That digital signature has to be validated as well. And this previous ID and index actually exists. And this is getting to your question, Emily. It still exists. But these inputs, once you've used them, they no longer exist in the database. They're kind of in the past. So that's the transactions. That's the core. I know it's like eating broccoli, but it's an important part of all of blockchain technology. The Coinbase transaction we've already talked about, so I'll slide over this quickly, but it's a reward for solving the puzzle. In the case of Bitcoin, it's solving the proof of work. Tom.
Sorry, can we go back to the miner incentive?
Mm-hmm.
It's like 0.1 or 20 Satoshis. And how is that different than the cost of trust when you use a financial institution as a
So Tom's question is the miners' economics. Of course, they get their 12.5 Bitcoin, and they might get some transaction fees. Tom's question is the other side. Why is that any different than paying some central intermediary? Anybody want to try doing this? I could cold call, but does anybody want to? I mean, this is an economics question about markets.
I would say that the person that is sending the transaction has the ability to choose how much will pay for that transaction. In the bank, it's regulated and you pay. And maybe that's one of the differences.
All right. So one difference is that the bank is setting generally a fixed fee schedule, and this is a decentralized market mechanism for setting fees. Sean?
The
fee for intermediary is a lot higher compared to Bitcoin. The transaction fee.
So Sean's second point is that currently, this may not be true in the future, but currently central intermediaries are able to charge higher fees than in this decentralized system. Ilan?
I think that conceptually it's not different from centralized intermediary. It's just the functions are the same, the amounts, maybe the amount that I pay, the amount of fees are different, but the concepts are the same.
All right, so Ilan is basically saying, well, maybe it's not so different. I mean, though it might be floating rather than fixed, it might be currently lower rather than higher, but you're saying fundamentally it's about the same. 1 minute, Shimon, let me just, I'm gonna, because you're like faculty, you're gonna actually tell us the answer.
The question is this mandatory? No, because
very good question. It's not mandatory.
So doesn't that could create a big misalignment of interest in the.
So it's not mandatory. Fees are market-based. And at times, like last December, they were really high, and now they're quite low. Partly because the Bitcoin network is not humming at full capacity. I mean, it can readily fit 1,000 to 2,000 transactions a block, and it's not like there's a jamming to get 10 and 20,000 transactions into a block, as there was last December. I'm sorry, Shimon.
I think it's very different in the sense that you're basically inflating the fee in most come through inflation, right? So even if when you don't transact, you're paying implicitly for other people transacting, and that's going to change over time. So that's actually kind of a clever mechanism of how structurally fees are going to shift over time in the network as it sort of hopefully matures.
Why don't I take one more here, Alexis? Yeah, we don't hear.
That's like when you have a central bank, for example, or an institution control transaction, like they're gonna keep the money and they could use it for like, I don't know, making profit on the like bid-ask spread or whatever. So they make money on a spread, whereas here, for the case of Bitcoin, like the money is going to stay in the system and it's going to flow to like another miner who's going to use it for another transaction. So it will stay within the same network, I would say, rather than like just going to another.
I hear you, but it might actually leave the network to lawyers like Patrick, right? Or it might leave the network if you use it at Starbucks, if Starbucks would accept it. So I'm challenging your thought, but you can challenge mine back, you know. Why don't we close out with Eric and then just move on?
The difference might be in the perspective from the person that's originated the transaction. It's basically the same thing, but if you think about it as a system, there's no single entity gathering all the money from transactions. You have a network, a distributed network of nodes that are getting that. And besides, once we get up past the 21 million Bitcoin generation cap, then all the system must be incentivized in some way, and transaction fees would be.
So Eric raises that two points other points, but two that I want to repeat. One is this is more decentralized possibly today than the current commercial banking system, for instance, for transaction processing, or the transaction processing that Visa and First Data do, which we'll study when we get to payments. So it's possibly more decentralized. I think you said it was more decentralized, but I'm putting the word possibly in there. And two is that, at least in Bitcoin's case, there's two revenue sources for providing the services. The miners do it for the coin-based transactions, 12.5 Bitcoin per block, approximately $80,000 per block currently. But also there's this little incentive of fees, which over time will have to grow as you go down. If it's only going to be 1 Bitcoin per transaction and then ultimately almost 0 Bitcoin per transaction, there'll have to be more Satoshis in the fee side. And some alternative coins, not Bitcoin, are more modeled on fees, and some coins are more modeled on mining rewards. They're not all, the economics, Satoshi Nakamoto, whomever he or she was or were, if it's a group, had to think through a bunch of economics. They've survived for 10 years. It doesn't mean that's the best set of microeconomics for a blockchain system. Tom, you look really skeptical.
But maybe this will be the moment where I take my 12-hour dive.
That's right. So you're about ready for your rabbit dive? Maybe. So the Coinbase transaction, we've talked a lot about. The reward, at least in Bitcoin, halves every 210,000 blocks. A very important thing that Nakamoto put in is you couldn't use your Coinbase reward for 100 blocks. So it was sort of stale or frozen for 100 blocks. I can think of two reasons, but maybe you all would think of another reason. Anybody want to give it a shot as to why you might do it? Joaquin?
Maybe you mine the block and you're trying to mine a block that shouldn't be, or it's not legal. You spend the money right away, so you can get.
This is the principal reason that's talked about not only in the literature but in the early blog post was, well, how many blocks does the chain have to go before everybody really thinks it's consensus? I mean, you could have said 5, 10, 20. Satoshi picked 100 blocks, saying that hopefully is pretty settled, or about 1,000 minutes. James.
If you can mine and then you can spend, couldn't you just perpetually create blocks and then pay yourself and create more and earn more and then keep building up?
So James is asking, could you just kind of game the system and keep mining and spending and mining and spending? No.
Will your rewards go down?
Sorry, Aviva?
Your rewards go down over time, so...
Well, that takes 200,000 blocks.
But if there are many of you doing that at the same time, then you accelerate.
So in some ways, that's what miners are doing, but they have to wait 100 blocks. And so that was what Satoshi was trying to get at. If you have to wait 100 blocks, it's probably now the consensus chain. It's probably been so validated, unless we got into the problem, Patrick, you weren't here, but some of the students raised this question, well, what if one country as large as China walled off their whole network? And just China went one way and the rest of the world went another. The theory of the case is that within 100 blocks or 1,000 minutes, somehow that would be discovered. But if it weren't, you might have a little bit of what James is raising as a question. But that's at least the theory of the case. It's always recorded as the first transaction in the Merkle tree. Highly technical point, but it has to roll up into that darn thing we were talking about, the data compression of the Merkle tree. And here's a little fun fact. You can add 100 bytes of arbitrary data in the Coinbase. You might say, why does he raise this? Well, because it's just a fun little place that some people express their creative wit, artistic stuff, send secret messages to each other. That buried in the Coinbase transactions, there's a whole forensics of fun little things that sometimes miners put in to the Coinbase. For those of you who are artistic, and the very first Genesis block had this sentence: the Times, January 3rd, 2009, Chancellor on brink of second bailout for banks. That was a headline out of the Financial Times that Satoshi Nakamoto put in the first block, Coinbase. It's just a little fun place that there's a playfulness that goes on amongst miners, sometimes talking to each other. Did you ever get a message? Did anybody?
Not that I'm aware of.
Not that you're aware of?
I know what you're talking about. There's one miner that likes to put Catholic catechisms in.
That has put in the whole catechism?
Does. In every block there's a little catechism that he puts in. It's a Legis mining pool. It's a small one. Yeah. So there you go.
There you go. And do they pay you in Bitcoin too?
Yeah, no, they're not a client.
Yeah, they're not a client. Okay. So it all rolls into a database called the unspent transaction output. These are the unspent transactions. If it's been spent, it's kind of burned. And Bitcoin transactions that haven't been spent fall into this. And you can use it. It's created because it speeds up the whole system. Instead of going back and looking for all these things, there's actually a database that has all the unspent transactions. I include in here what I find is a sort of interesting revelation or irony. When Satoshi built Bitcoin, and for the 16 versions that have come since over the 10 years, all the developers, the Bitcoin core developers, have kept the unspent transaction output not on a blockchain specifically, but in a database called a level DB database. So those of you who are closer to computer science than I could say all the pros and cons of a level DB database, but I'm just observing that even within the most used first central database for blockchain called Bitcoin, they chose to use not a blockchain, but in essence a more standard database to keep the unspent transaction output. Now, in a sense, it's all part of this blockchain solution. I'm just saying it's one database within the blockchain world that's actually not a blockchain. Helene, did you? Yeah. It's just like sort of an interesting irony, but it also sort of says economically and technologically, Satoshi was trying to create a money system. He wasn't trying to use blockchain for every bit of data. So this is the actual size of the unspent transaction output. If you can't see, I think it's about 50 to 60 million. It was higher, so there was about 60 million unspent. It's not 60 million Bitcoin, because there's about 17 million Bitcoin. So you could average it out. You could say, wow, each transaction has less than 1 Bitcoin. Well, actually, there's been surveys and studies shown that about half of these 54 million transactions are so small that they go by the term of they're called dust. That there's so few Satoshi that it's not even worth the fees to try to redeem them. They only add up to less than 0.5% of all the outstanding Bitcoin, but they're just dust. So maybe out of these 54 million unspent transaction outputs, half of them will never be used because it's not economically worthwhile. It's like the pennies in the top dresser drawer that you all might not spend. There's the similar thing here. Hugo?
Yeah, I guess I have a question about that. It might not be feasible now, but like maybe with layers on top of Bitcoin, that people can do these microtransactions. Because like our pennies might be worth like a lot of money, and then.
So Hugo is raising that just like the pennies in your top dresser drawer might be worth something one day, what I'm referencing is Bitcoin dust. About half of these unspent transaction outputs, a Satoshi here, 10 Satoshi there, might one day be worth something. Good point. It's just like the pennies in your top dresser drawer, though. Have you lost them in the meantime? Like they might be worth something, but in the meantime, have you lost the private key to those little Satoshis? I put on here 3 moments of time just to give you the sense of the actual number of transactions that have happened. There's been 342 million transactions on the Bitcoin network today, or as of a day or two ago when I put the slides together. So of the 340 million transactions, only about 54 million are still outstanding. The other 290 million have been spent, if you wish. Yes?
So then where are these outstanding transactions stored? Like if they're not, are they still being included in the blocks themselves when you add them to the
Which outstanding transactions? The 54 million that are still available? The 54 million all reside in a database within the Bitcoin software called the Unspent Transaction Output, UTXO. And UTXO, these aren't letters I'm making up. That's a database, 54 million transactions. Separately, they are actually in the blockchain itself. So all 340 million transactions that have ever happened are in the blockchain. But to make it easier for the software, the 54 million that have never been spent or reside in a software. Does that answer the question, or work with me?
It's a distributed database amongst all the different nodes.
Correct. All the 10,000 nodes all 10,000 of the nodes can have the full UTXO set. Some wallet providers have the full UTXO set, but they don't have to. Somewhat lightweight nodes usually don't, but can. But a lightweight node would never want to have all 340 million and the full blockchain. So in essence, they're in multiple places because they're in the full blockchain on 10,000 nodes, and they're also in the UTXO, not only on the 10,000 nodes, but occasionally elsewhere. Aline.
So I heard you say the word spent transaction, which is a bit misleading because a transaction can be spent and not spent. Because for example, we have two outputs. One output is spent by a future transaction and the other output is not spent. So it's a bit misleading to say spent transaction because that only happens when the transaction has only one output and that output is spent.
Well, I'm using it lightly. I'm saying that of the 340 million transactions that have happened, 290
have an output that is spent. Or what are you saying exactly? Because transactions have multiple outputs. They might have n, and maybe k of them are spent. So the other outputs are unspent.
I'm saying there's 340 million. If I did my data search correctly, and I'm fallible, so I might not have, but if I did my data source correctly, there was 340 million previous outputs. 290 million of them are gone.
Okay, so outputs. So then you should say transaction outputs, because those are different than transactions.
Yes, except for it was easier to put TXS. But yes, Aline's clarification is, I believe, accurate.
So people can understand that there's a difference between a transaction and a transaction output.
In essence, what Aline's saying is there's currently 54 million transaction outputs in the UTXO, which also says outputs. There had been in the past another 290 million outputs that have already been spent. We together? So there's a scripting language. There's a little bit of computer code. And there's no need, I said there was no prerequisite to take any computer science before you were here. And my own computer programming is so old because when I was programming, it was in Fortran and APL. And you can look that up. It's kind of like around with cuneiform and you know, the Rosetta Stone. But Satoshi Nakamoto decided to put a little bit of computer programming inside. And I'm not going to get the count right, but there's several hundred, but not several thousand little operations and codes that you can use in the Bitcoin script. It's not Turing complete, which means you can't do a lot of the things that you can do in all the rest of computer science, but it's more secure. In essence, it has fewer attack vectors. It's harder to bring down a little bit. It's a programming code, as I said. For those interested, it's called stack-based, where you sort of move the code over one at a time as it's being performed. And it gives some flexibility. And back to Emily's question about why there was lock time, or Shimon's, scripting code allows for some conditionality. That it appears that Nakamoto was trying to give some ability to condition a transaction on events, but not so much conditionality, so much flexibility that he needed a Turing complete. So he kind of, I'm going to say, chose a midway place. You could have created, I believe you could have created Bitcoin and say there was no scripting language. It was just going to be a straight instruction moving this output, or this input to another output. Created a little bit of computer code, but not a lot. And that's what I think about sort of the economics and the marketplace for this. And next Tuesday, when we talk about smart contracts, And I promise you, there's a reason for the craziness of my talking about Turing complete and scripting code. It's because next Tuesday we'll be talking about smart contracts where they're much more flexible. And so this is sort of the foundational, and you don't need to know anything more about computer science than you want unless you go with Tom down that rabbit hole and spend more time reading. So there's 4 different types of, I call them script types. They're not actual script words, but you will read about these from time to time, and I just wanted to cover these 4. The UTXO, remember, is about 54 million transactions, and there's been a nice academic paper that I didn't assign that was written earlier this year that investigated the whole 54 million, all of the unspent transactions. And this is how it broke down. 81% are transactions that send to a hash of a Bitcoin address. 8-9 years ago when Satoshi created this, that was not the most popular instruction, but it's basically sending an output to the hash, the compression, the commitment of a Bitcoin address. We're now up to 18%. This didn't exist 3 and 4 years ago, really, but 18% go to a conditional script. It's a hash of a conditional script. So somebody's saying, Emily, it's not even about time. It's like you can only get it when all these other instructions that are in the scripting language happen. And I'm going to hide the conditions in a hash of it. And then only 0.7%, only 0.1% goes the way that he first envisioned 9 years ago, directly to a Bitcoin address. So it's either to a hash of a Bitcoin address, a hash of a conditional script, and a little less than 1% now go to multiple signatures, meaning you need 2 out of 3 or 3 out of 5. Or believe it or not, this academic paper shows that some say 0 out of 1. Now, it's hard to believe that somebody mistakenly programmed something to go to 0 signatures, but apparently somebody did. So I just wanted to give you a sense. There's some flexibility in the computer code, not a lot of flexibility, but just enough that you can do things that are really helpful. And they're going to solve a lot of challenges for Bitcoin. Hugo mentioned layer 2. We're going to be talking about layer 2 later in the semester, where there's a whole way to put technology on top of Bitcoin. And it's because the scripting language is there that you can do that. Any questions on script? I know I'm trying to cover a big, weighty topic in, 120 seconds or less. No. So just back to the whole, this is just a review. What have we talked about? There's that little graphic again. The time, it's just a bunch of blocks. That's what a blockchain is. Though today we realize that underneath the blocks, we have another chain. I often think of 2 chains. The chains of blocks. In Bitcoin, there's about 500,000 blocks. But underneath that, there's all the transactions that are in fact chained as well. 54 million of those outputs have not yet been spent, and 290 million have already been, outputs have been spent. But underneath about 500,000 blocks, there's been 340 million, outputs, so to speak. It creates a database. Bitcoin is a transaction database. Next Tuesday, we'll talk about an account-based database in Ethereum. But it could be a ledger, which is transactions, or a ledger, which is balances. Satoshi Nakamoto decided to do transactions here. In some ways, I believe it's because it was fewer attack vectors. Probably a little bit more secure, but I'm not entirely sure. And until you solve the riddle as to who Satoshi Nakamoto is, we won't know the answer. Of course, hash functions we talked about, and digital signatures, and a consensus protocol. So I like to think of it in 3 buckets, whether it's for dinner party conversation or digging into 3 lectures. It's the cryptography itself. We did that last Thursday. And if you have to remember anything, it's only 2 cryptographic primitives. Hash functions and digital signatures. How many people think they kind of roughly have what a hash function is? All right, so I lost half of you. All right. Is there anything I can do for Lauren's table? I didn't see a single hand go up. And Lauren, are you reading your Facebook page, or are you like listening to the class? You've got your computer open. What's your name? Matthew. All right, that might have been that you weren't listening to the class. Thank you. How can I help on what a hash function is? My promise is to bring everybody along. Nobody at your table said you even roughly got what a hash function is. What's your? I'm not trying to embarrass anybody. I'm trying to work this through to get it's Nicholas. Yeah. So, give me a baseline. Did you read any of the readings? Maybe not. Okay.
I have, yes.
You have. Okay. Hash functions came along decades ago to help facilitate database management. Sometimes it's called a registry. It's taking a lot of data and shrinking it down, compressing it, shrinking it to maybe a series of numbers. I think of it sometimes as a zip code for information. Down in Baltimore, Maryland, I'm in 21220. Well, I grew up in 21208. It was my parents' zip code. I won't say my current one. We're being videoed. And so I think of it a little bit like that. So a hash function has nothing to do with Bitcoin, came along to take a bunch of data and create a registry. But through that, it also became a way to do a commitment. Yes, your first name?
Dana.
Dana?
Yeah, Dana. What goes into the hash function and comes out as a hash? That's what I don't understand.
So what goes in is any set of data. Today, that could be an entire movie. It could be a picture of everybody in this room. Initially, it was mostly alphanumeric data. But because in computer technology, all data can be broken down to a series of registries of zeros or ones. I mean, computers started with literally, the first ones started with registries that were either turned on or off. If they were on, call that a 1. If it was off, call it a 0. I'm not sure which way it goes, but I keep looking at Aline. And so all data can then be brought down to a series of zeros and 1. And if you put 4 zeros and 1s in front of each other, 2 times 2 times 2 times 2, 2 to the 4th is 16. All of a sudden, you see if you keep going 2 to something, you can get a lot of data. So back to your answer question, Dana, when we talked last week about the New York Times crossword puzzle, New York Times may, if they wish, take the solution of their crossword puzzle and hash it. And then, Stephanie? Stephanie likes to do the New York Times crossword puzzle. And she wants to know if she properly completed the New York Times crossword puzzle, the New York Times could say to her cell phone, we're not going to really give you the answer, but we'll give you the hash of the answer. And then when she's finished and she pushes a button, her application could say whether her answer properly hashes to theirs.
Can I ask a follow-up?
Please, please, we're trying to learn here together.
In the case of a blockchain, it's whatever data you've loaded to the blockchain, and then in Bitcoin, it's just the transaction. Is that right?
So in Bitcoin and blockchains, they use hash functions in several big ways. Everything you said was correct, but except for the one thing when you said it's just, because they actually use hash functions in the middle of the proof of work, because the hash pointer points, block 3 points to block 2, and there's hashing. They use the hash function to compress a bunch of data. what I call the Merkle tree, but it's taking 1,500 or 2,000 transactions and squeezing it into one hash. So they're hashing all of these things up. It uses hash functions in the midst of the Bitcoin address. The hash function is like electricity in the middle of it almost. It's probably used 6 or 8 places, and some I don't in any way know myself or need to understand. Nicholas, how are we doing? Did we get a little closer?
Yes.
Lauren, did we get a little closer?
Yeah.
Matt?
Oh, yeah.
You're there. You're there.
I'm not there yet, but I'm closer.
Stop by. Send me an email. It's gensler@mit.edu. I'm here like 4 days a week. Ben?
So I think the time that I really understood hash functions was when I saw someone do a live demo. There's a website called brainwallet.info, and you can type in text, and in real time it converts it into a hash.
Okay, so say the website again, Ben.
It's brainwallet.io.
So brainwallet.io. A recommendation.
And I've just Googled brainwallet blockchain, and you can type in text, and you see in real time it converts it into a Bitcoin address, and you change one letter, or make one in uppercase or one in lowercase, and it changes in real time. And it's just you put any text in, you put password in, and it turns it into a blockchain address, and that's all a hash is. It translates text into a hash.
Or a whole movie. We talked about the network consensus, how to actually agree on the state of information with no centralized authority. You don't have a central bank or a commercial bank or a Facebook or a parental unit, if you wish. It's all of us out there on the playground figuring it out together somehow.
Sorry, I have a question here. For the proof of work, my question is, for example, I make a transaction. Does it mean I have to wait for 10 minutes for the transaction to be completed? Or it's like, for example, when we do Venmo, it's like instantaneous. I can immediately get the results, but
so Anton's question is, does it mean I have to wait 10 minutes? Venmo and so many other payment practices can go more quickly. The answer to you is yes, and that is one of the commercial challenges to blockchain as we know it in Bitcoin. There are certain approaches to that, layering in technology on top of it called Layer 2 or Lightning Network. We're not going to dive into Lightning Network, but everybody should hold on to Anton's question. It's the right question that if all of you bring your critical reasoning to this class about markets and about commercial realities, a little bit about the law and a little bit about technology, because that's what we're trying to do. It's like, oh, well, does this really matter? Will it work? Hugo.
So just point of contention there.
Contention.
A little bit.
Oh, very good. I like that.
So if you know the person that you're transacting with, you can accept a transaction with 0 confirmations. As long as it gets into the mempool and has a reasonable fee attached to it, then it'll eventually get included in a block. And that's probably good enough for most people.
So what Hugo is saying is another approach is to take counterparty risk. Back to Anton's question, does it mean you have to wait 10 minutes? The actual technical answer to that is no, you don't have to wait 10 minutes unless you want final settlement. If you want finality with no counterparty risk, no commercial risk. Hugo is saying, well, if I'm willing to take some economic or commercial counterparty risk, which is in finance, you take it all the time, then maybe I can do it less than 10 minutes. And in fact, even Starbucks, when Starbucks accepts your credit card swipe, they're taking a little bit of counterparty risk from the payment processing company First Data. Or I don't mean to say that it might not be also from Visa and the banks, but I'll just say the payment system has some counterparty risk because final settlement in our payment system doesn't happen within seconds. So the actual answer, thank you, Hugo, clean me up again. You should do this all the time. Everybody should clean me up. it's that final settlement can't happen, and so you have to find other solutions, whether it's some commercial arrangement with counterparty risk or other technical commercial arrangements. Shimon.
Well, yeah, make the counter argument, which is that 10 minutes is not final settlement, right? Because it could be forking. So if you want to be, it's basically the probability of the finality goes up with time, which is associated with how many blocks are attached to.
So Shimon's point is that even in 10 minutes, your probability of finality is not complete because the block might not be the block that's included in the longest chain. And many people have said you maybe should wait 3 blocks or 6 blocks. I think the longest, I'm going to use the term loosely, orphaned chain has been 5 blocks long. In Bitcoin, what's the longest orphan?
It was an accidental fork. It was 20 or more blocks. Due to some crazy things that miners were doing, they accidentally forked the blockchain.
Okay, what year was that?
So look up March 2013 fork, and there's another fork after that in 2015 maybe.
Yeah, somebody's been down the rabbit hole. All right. But there's some still probabilistic risk. Aviva, and then we'll move on.
What's the fork?
So I don't have the chart up, but if you remember, there was the slide that showed the longest block. It was in black, and it had little purple blocks. That's a fork. There's some forks that end up being that both chains continue for a long time. They're called hard forks, and there is something called Bitcoin and Bitcoin Cash have come out of that. Most, the way that Aline was using it, are discarded. I'm sorry, behind. Remind me your first name?
Aaron.
Aaron.
So this might not be, I don't know, let me know if it's not the right time to ask this question. I'm getting a bit confused between the difference, or the most important things we need to know and the differences between the technology of mining Bitcoin versus just transacting, like on the blockchain. Because I'm not sure if there's like some major differences we need to, or what are the major differences we need to understand?
Very good question, Aaron. Aaron's question of what do I need to know about mining? What do I need to know about transaction? Is it one of the same? I apologize. They overlap, but they're not the same. So think of a Venn diagram but it's a very good question. The essence of mining is creating an incentive structure where there's no central authority to validate and put a new set of transactions or data, I'm going to say broadly data, into the ledger, into the accepted state of what reality is. So mining helps with that. That's that whole process. In essence, who gets to decide the next block of data? Transactions are included in the data, but it's not identical. Mining is really critical, but it's not the only component. In terms of transactions, then you have to actually think of, well, there's this other thing going on. Well, there's been 340 million of these in the Bitcoin network so far. And has it been used already? Has it been spent? Does it have an appropriate digital signature? If there's a time lock on it, is there a condition? Might there even be this little bit of scripting code that puts other conditions, like there has to be multiple signatures? Has it been double spent? So I wish it was a very good question. They overlap a lot. One thing you can just remember is mining is about that there's been 500,000 blocks. Transactions, there's been 340 million. So there must be something else going on in all those transactions. Does that help a bit? Kelly?
Since we're talking about all of the technical features and how they overlap, one of the questions was what part of blockchain is novel to Satoshi?
Mm-hmm.
Is it
is the novelty in bringing it all together, or is it one specific thing? Because, you know, the paper talked about like the ledger and creating the incentive and then sort of solving the whole Byzantine generals problem that I don't really understand. Was there a specific thing that unlocked the...
So Kelly's question, which is the heart of the study questions, is what makes the whole Satoshi paper novel? Is it just bringing it all together? Or is there something more? I'll give you a hint. I think there's one other thing. I think that genius can be just in bringing together things. That in itself can be sheer genius.
I mean, there's also the part that, like, creating the value in the currency, but I don't know if that's...
Right, so creating an incentive structure within in there. Others, Derek.
Yeah, I had a question. So how...
Question or answer to Kelly's question?
No, I had a question.
All right, I'm going to hold your question, Derek, just for a second. Who's going to help me with, because it's like central to the study questions. Okay.
Another thing to add, the proof of work that Satoshi did on the consensus mechanism, it's also novel.
Yeah. But novel, though, didn't Adam Back already do some of it in Hashcash? So its application was novel. So that's where I come out, where I think the genius is bringing it all together and using Adam Back's proof of work in a way that really addressed double spend. Adam Back was not dealing with a double spend issue. He had different challenges. It was about email spam. Frankly, it didn't even work with email.
Because I knew we weren't counting the proof of work as a completely novel thing, because the article discussed how it was already published, but I guess it's the application.
It's application specifically to the double spend. So I kind of think of Patrick Merck. Would you answer it? And how would you? This is somebody who ran the Bitcoin Foundation, but he's a lawyer, you know. But
no, I think that's absolutely right. So usually, and I think they address it in that particular paper, when somebody says, what was the thing that was different about Bitcoin from everything else, the answer is Nakamoto consensus, right? And Nakamoto consensus being the incentive structure, pulling everything together and aligning everybody to actually create trusted signing parties for this database, which you couldn't without having to actually trust or identify those parties, right? And that's something that really hadn't existed before. And so that's really novel. That's sort of the breakthrough that I think you can attribute to that particular white paper. I also use this as a way to give a clean definition of blockchain, which is a badly abused term, as I'm sure you'll discover through the rest of this class. As saying, to me, a blockchain is something that is born from Nakamoto consensus, right? Blockchains, as they discuss in that paper, have existed for decades, right? Like, that's not even novel data structure. But using that to form Nakamoto consensus, that's the thing, right? It always sort of comes back to that. That's, anyways, maybe a longer elaboration.
Good. There we have it. You now know that you're in a class that has guest speakers. I do want to say on the guest speaker point, and Derek, I'm cognizant you have a question, but we have 12 minutes, so I just want to, or so. Next Tuesday, Larry Lessig, who sometimes floats into this class, has agreed to guest lecture with me. And so we're going to co-do smart contracts. And let me just say a little bit about Larry. I mean, you sort of see him here. He bicycles over from Harvard. He's a constitutional scholar that's a remarkable constitutional scholar, and you don't get to be a full professor at Harvard. They stole him away from Stanford, actually, where he was a full professor too, readily. But he's extensively written. Anybody in here a West Wing fan, the television series West Wing? So he is the only, or do you know that Larry Lessig was in West Wing? Now you do. Well, Larry was, and Christopher Lloyd played Larry Lessig in one episode. But you'll go back and you'll find the episode. And Larry has a funny story about watching the filming of it. But Larry's a constitutional scholar over at Harvard. He clerked for Justice Scalia on the Supreme Court. He clerked for Posner over in Chicago. He knows a lot about contracts, and so I asked him if he'd help teach smart contracts next Tuesday. So we're gonna Mutt and Jeff it up here next Tuesday. Watch out, Patrick, you might be up here one day. This is not a class that we're going to have a lot of guest lectures. Later in the semester, I hope we're still in confirming Jeff Sprecher, who's the Chief Executive Officer of Intercontinental Exchange, runs the New York Stock Exchange. Jeff is probably joining us on, I think it's November 15th. But I really want to stay to like the content and so forth. Derek, what's your question?
I can follow up with you.
Okay, follow up. All right. And then we just did transactions today. Remember the hash functions, the New York Times. We're in a little better place with Lauren's table now. All right, good. My goal is not to embarrass anybody when I ask these questions. My goal is that we all come along on this journey and that we somehow have some basis, because it does relate to understanding the commercial reality and the economics. We talked about the time stamping and the blocks, the Merkle trees, which is not a deep part of it, and of course digital signatures. Part of the reason I replay this each time is because in politics I of course learned that repetition is a really important thing, but I also think it's true in academic settings. And then Bitcoin addresses, and that's just a cleanup that it's not identical to a public. And then the proof of work, and back to the questions. Nakamoto consensus is yes, all of this and an incentive structure, but it's this proof of work. And to Aaron's question, proof of work is a little bit different than the transactions that we talked about, but there's a lot of overlap. And then it creates the native currency. And I've corrected the slide to 2140, of course. The network is really critical too. And that there's all these different actors on a network, 10,000 nodes and this many light nodes and the miners and the mining pool operators, and they all have their separate economics. And so if anybody wants to come and get office hours, talk about those economics, please come on in. If there's nothing you remember from the reading, I've now read this paper probably 6 times to kind of slowly get it through my head. But every time I read the Clark paper, I go, wow, that really helps me, because it's not like Satoshi Nakamoto just flipped his fingers and it was on the backs of a lot of cryptography, a lot of technology earlier. But this is the chart I turn back to, and it sometimes helps me. There's time stamping, there's digital cash, there's proof of work, and how these things. Maybe 10 years from now, they'll look back and Nakamoto's stuff will just be built upon. That's the central question. That's what some of our colleagues are doing over at the Digital Currency Initiative or over at the Computer Sciences Lab. They're saying, can they build upon this and take it to another level? Right now, and you'll see throughout the semester, there's not a lot of full-scale applications of this technology. But it might just be in a whole line of this. Yes, and I can't remember your first name. Aviva?
I'm Aviva.
Aviva.
And that is the other Indian movement.
That's the other Aviva.
That's the other Indian movement.
Yeah, it's important. Out of 100 people, we can have 2 Avivas, you know. We could even have 2 Avivas if there's 2. What's that?
Priya. I'm Priya.
Priya. Oh, Priya. Oh, I'm sorry. Thank you.
So I was just thinking about, like, is one of the applications of the hash function. So does the hash function actually replace the data? So I'm thinking now that everyone's, saving data in the cloud. So can you save a hash function instead of your actual data, and then so it can be compressed and then?
Very good question. My summary of it, though others would probably be more expert, my summary is you get a choice. You can do either. So let's take it in blockchain rather than in the cloud. You can choose to save in a blockchain just hashes and have the full picture somewhere else. Let's say you were going to do a whole database of...
A library.
Of what?
Let's say like a library.
A library. And so there's 100,000 books in the library. You could hash all 100,000 books and then store the hashes in the blockchain and not the books themselves. And that would form a blockchain of the commitments to those books. Or you could actually, I guess, put the books themselves into the blockchain. Now, I saw some shaking heads in the middle. Aline from the Digital Currency Initiative.
The way I understand The answer is no. You cannot actually, you can you can store the hash that doesn't replace the data. The storing of the hash allows you to prove that you have the data. But you cannot, like, the fact that you store the hash doesn't mean that you store the data.
But Aline, there's like a two-part question. You can never get rid of the book. You shouldn't get rid of the book because hashes are one way. You're not able to take the hash and recreate the book. You can't take the hash and recreate the New York Times crossword puzzle. But you don't need to store them in the same place. And I was asking, so it's thank you, because it's two parts of the question. You could store the hashes in the cloud and store the book somewhere else. But you still need to store the book, maybe. Is that? So who's Satoshi Nakamoto? We have just a handful of minutes, but can every table, each table is going to take 4 minutes, and amongst yourselves decide who's Satoshi Nakamoto. So how are we doing? Who's your answer to Satoshi Nakamoto?
We would say probably multiple people led by Hal Finney.
Okay, so the first one is multiple people probably led by Hal Finney. Hal Finney, H-A-L-F-I-N-N-E-Y.
Something like within the government or a government?
So table number 2 is government actor, U.S. or foreign?
I don't know if it matters, but maybe U.S. Yeah.
U.S., but it might not matter. How are we doing over here? Dorian Nakamoto. So you're going with the Newsweek story. Yeah. Priya, sorry about the name thing before. Your table, where?
CryptoPunks.
What's that? A bunch of crypto punks.
Plus economists. It's like a group of people.
So a group of crypto punks and economists, and how do you spell crypto punks, though? Cypherpunks. Cypherpunks, actually. Cypherpunks. Where are we here?
NSA.
Oh, the NSA. All right.
People with incentive and the capability.
Oh, so incentives and capability, you think it's NSA?
MIT.
MIT. Oh.
We said a guy named Gary Gensler.
There's a word for that, but I can't say that on tape. Kelly, Anton, two Alines. What do we have here? Jihi?
Let's go in Nick Savo.
Nick Sabo, who is wrote the first paper on smart contracts. So Aviva is Nick Sabo. Oh, my hash table. I mean, who do you go for?
We actually did have him. Nick Sabo.
Oh, all right. So another table, you can say that it's another table for Nick Sabo. You can put another vote next to him. Here?
We were going with you, Gary.
No, come on.
All right, we think it's Craig Stephen Wright.
No.
Craig Wright, the Australian. Oh, my God. Oh, Patrick Burke's table is going to go last. Here?
Bill Belichick.
What's that?
Bill Belichick.
Bill Belichick. Alan Greenspan? Alan Greenspan. Now, I actually know Alan. He's really talented, but I don't think Andrea would let him do this. Here? Who do we have?
Me?
Yeah.
Kenta.
What's that?
Kenta.
Who?
Kenta, me.
No, but who? You're saying you invented it? No, this table. This table
is saying him.
Nick Sabo. So another for Nick Sabo. So does anybody want to tell us why it's the NSA? Oh, Patrick Merck. I'm sorry. What's this table?
Well, as I said, I don't know. And if I
Yeah,
know,
really.
I would say that I don't know. So, and I would create as much obfuscation as possible. So I think it was like the worst person to have at a table for this, and I did them nothing but a disservice in their hunt for Satoshi. But I'll let somebody else speak. No, I don't.
But if he did know, he would say he doesn't know. Derek, who did your table go for?
We said Craig Wright.
Craig Wright.
You can see my influence.
Oh my gosh. So So let me ask this, because it's just for fun, 1 minute. Somebody said that it was the NSA. Do you want to say why?
Because arguably they have the most advanced cryptography in the world. And if anybody was doing this, to have a system where all the dark money in the world was flowing around, instead of $100 bills, you would create this and create it in a way where you could hack it backwards and figure it out. And they have the capability.
Wow, Hugo.
I mean, more money is going from an error right now than it is to Bitcoin.
All right, so Hugo would say that if it was the NSA, it didn't work out for him too well. And those of you who said Craig Wright, I heard some others in the room that said no. So who said Craig Wright? Which two tables said Craig Wright? Why'd you pick Isabella and Ben? Why'd you pick Craig Wright?
So I read up on this a bit, and basically like, people analyze the English used in the email, and they think it traced back to Australia, and then we Google from there.
All right, so just the language analytics for Craig Wright, and those who said it can't possibly be Craig Wright. Who did that? Aline.
Yeah, so he started a website and he said, oh, here's cryptographic proof that I'm Satoshi Nakamoto. But he actually botched it. Like, if you are Nakamoto, you can prove you're Nakamoto by spending the first coins. But he couldn't do that, so come on, man.
So Aline says he failed the test. He didn't spend the first coins from 2009. 3 tables picked Nick Szabo. Why'd you pick Nick Szabo? Just any one of the 3 tables? Because we're going to talk about him in the next lecture? No? All right, look, this was a bit of fun. I just thought it'd be worthwhile because the only person in the room that really knows who Satoshi Nakamoto is isn't going to tell us. But you're welcome back anytime. Thank you. I will see you next Tuesday. Remember, Larry Lessig is here, so please do the readings. Please, let's have a good time.